Remember, forces are vectors. The electric force is a vector. So far, we've been treating our electric force as a vector in one dimension. But last semester, we learned, of course, that vectors can come in 2 or 3 dimensions. So let's remind ourselves how we treat vectors in 2 dimensions. Here I have my x and y axis. I'm going to draw a vector in 2 dimensions. I'm going to have my vector pointing off in this direction, kind of like so. Okay, this is my vector A. Now, the x component of the vector is this whole part of my vector right here. This is what I would call A sub x, the x component of my vector. This part of my vector right here is the y component of my vector. Okay? And the components of this vector then make right angles with each other. So we have a right angle triangle with 2 legs, y and x, and the hypotenuse, which is the magnitude of this vector, the size of this vector. Okay, so there are a couple of different ways we can write this vector. We could say that our vector A is equal to the x component of the vector in the I hat direction, which is along the x axis, plus the y component of the vector, which is along the j hat unit vector, or that means the y axis. So we could write our vector here in unit vector notation. This ax component, that's the x component of my vector along the x direction. That's the I hat direction. And then I have the y component of my vector, which is along the j hat unit vector, which is along the y-axis. We can also get the magnitude or the size of this vector. And we can do that by using the Pythagorean theorem. I'm going to use a different marker. I'm going to call this side of my triangle the hypotenuse C. I'm going to call this leg of my triangle A. I'm going to call this leg of my triangle B. And with our Pythagorean theorem, a squared plus b squared is equal to c squared. C is the hypotenuse of the triangle, A and B are my 2 legs. So we could solve this for the hypotenuse of the triangle by taking the square root of both sides. And if we do that, the hypotenuse of my triangle is the square root of a squared plus b squared. Okay. Now, if the magnitude of my vector is this side of my triangle, then I can say that the magnitude of my vector A is equal to the square root of my ax component squared plus my ay component squared. That's how you get the magnitude or the size of this vector if you know the x component and the y component of your vector. We can also find this angle here, theta, by using tangent. Tangent of my angle theta is equal to the opposite side, which is ay, over the adjacent side, which is ax. So if I know the x and y components of my vector, I can get this angle theta, the angle that that vector is with respect to the positive x-axis. I can take the inverse tangent of both sides, so my angle theta is the inverse tangent of ay over ax. So to recap, we saw how we can write this vector in unit vector notation. We saw how we can find the magnitude of this vector. We saw how we can find the angle that this vector is with respect to the positive x-axis. We can also figure out what ax is and ay is if we know the magnitude of A and we know this angle here, theta. And we can do that by thinking about sine or cosine. So let's start with my angle theta here, and let's think about cosine. Cosine of my angle theta is equal to the adjacent side, AX, over the hypotenuse, which is the magnitude of my vector. So AX is equal to the magnitude of my vector A cosine of my angle theta. And by the same similar argument, if we use sine of theta, sine of my angle theta equals AY over the magnitude of A. So sine of theta is equal to the opposite side over the hypotenuse. And I can solve this for AY. So AY is equal to the magnitude of A sine theta. Okay, so we're going to use these different relationships whenever we work on vectors in 2 dimensions. And the final piece I want to talk about here regarding vectors to refresh your memory is the addition of vectors. Let's say we have 2 vectors that we're going to try to add together. Let's say we've got vector A and we want to add it to vector B, and that will give us a vector C. When we add vectors together, we add up their x and their y components. So in unit vector notation, we can write vector A as ax I hat plus ay j hat. We can write vector B as bx I hat plus by j hat. So if I'm adding up 2 vectors to give me vector C, then I can say that vector C is equal to, when we add up the components of the vector, ax plus bx I hat plus ay plus by j hat. So this component, ax plus bx, is also the x component of C. So I could say that that's also equal to cx. ay plus by is giving me the y component of C, a new vector. So I could call that cy. And then I could also write C is equal to cx I hat plus cy j hat, where cx is going to be ax plus bx, and cy is going to equal ay plus by. And we're going to use vector addition like this, and also breaking down our vectors into their x and y components, and thinking about the angles of those vectors with respect to the positive x-axis in order to solve some 2-dimension electric force problems. Suppose we have 3 charges lined up on the x-axis. Our first charge is at a position of x equals 0. Our second charge is at a position of x equals 1.5 meters. Our third charge is at a position of x is equal to 2.6 meters. And they have charges of Q1, 36 microcoulombs, Q2, minus 30 microcoulombs, and Q3, 36 microcoulombs. Our question that we have to answer is, what is the net force in newtons on the third sphere? So, the net force, remember that forces are vectors, and our electric force is a vector, so we are going to get a vector for the net force on charge 3. Okay? The vector is going to have a magnitude, a size, and a direction. But at least for this problem, we are all operating along the x-axis, so we only have one dimension, the x dimension, that we have to worry about for this problem. Whenever I solve these types of problems, I have no idea. how you might solve a problem like this without drawing a diagram. So that's why I always start with drawing a diagram. And instead of making a table of my knowns and unknowns, you could do that. I just go ahead and label my system with my knowns and unknowns, and that would give me, full points for, strategic approach and writing down your knowns and unknowns, because I've got it labeled here in my diagram. Okay, so let's see. We need to find our net force F3. Let's think about all of the forces that are acting on our third charge that are going to add together to give me the total net force on my third charge. That total force we're calling F3. Okay, so let's think about the force that my first charge is exerting on my third charge. So Q1 and Q3 are both positive. Okay, so that means that the forces between these two are repulsive. They want to push away from each other. So the charge that Q1 exerts on Q3 is going to try to push them away. So the charge the force that charge 1 exerts on charge 3 is going to be pointing off in this direction. And I'm going to call that F13. That's the force that charge 1 exerts on charge 3. Now, what about the force that charge 2 exerts on charge 3? Charge 2 is negative, charge 3 is positive. These are opposite signs, and they're going to want to attract each other. Okay, they're going to want to move toward each other. So the force that charge 2 is exerting on charge 3 is going to make them want to come together. And so that force that charge 2 exerts on charge 3, which I'm going to call F23, is pointing off in this direction. So F13 is positive, F23 is negative. To get our total force acting on charge 3, we have to sum up F13 and F23. And we see that F23, since it's pointing in the negative direction, we'll have a negative, we'll place a negative sign on it, okay? The first thing that I always do when I think about these types of problems is to think about the direction of the forces in the problem. We've just done that. We were thinking about all the forces that are acting on charge 3, okay? And so we've figured out those directions. Now we know what sign we need to place on those vectors. And so now all we have to do for this problem is to get at the magnitude of F13 and the magnitude of F23. So let us do that. And we're going to use our equation for the Coulomb force, or the electric force. So F13, we'll just think about the magnitude right now because we've already talked about what the sign should be. And that's going to equal our Coulomb constant times Q1 times Q2, Q1, Q3, yeah, Q3, all over the distance between them squared, okay? So then this is going to be our Coulomb constant is 8.99 times 10 to the 9 Newton meters squared over Coulomb squared. And then we're going to divide it, or multiply it by the absolute value of Q1, which is 36 microcoulombs. So we'll write that as 36 times 10 to the minus 6 coulombs, and then we multiply it by the absolute value of Q3, which is also 36 times 10 to the minus 6 coulombs. Okay, I know it's almost running off of the edge of my screen here. And then we have to divide that by the distance between charge 1 and charge 3. So if I come back over here to my drawing, I see that charge 1 is at 0 meters, charge 3 is at 2.6 meters, so the distance between them is 2.6 meters. So we've got divided by 2.6 meters squared. Okay, we'll plug all those into our calculator and we will get the magnitude of 1.72 newtons. And that's the magnitude of F13, the force that charge 1 exerts on charge 3. Now we'll do the same thing for the magnitude of F23. Okay, so F23 is going to be our Coulomb constant times Q2 times Q3 all over the distance between them squared. So again, that will equal 8.99 times 10 to the 9 Newton meters squared over Coulomb squared times our charge on Q2. We're just thinking about the absolute value of it. So that charge is 30 times 10 to the minus 6 coulombs times Q3, 36 times 10 to the minus 6 coulombs, and we divide it by the distance between them squared. So we're thinking about the distance between Q2 and Q3. Q3 is at 2.6 meters. Q2 is at 1.5 meters. So 2.6 minus 1.5 gives you 1.1 meters. So they're separated by a distance of 1.1 meters. That's what goes here. We're going to square it. And that equals 8.02 newtons. So remember, that's just the magnitude of this force. You would get the question wrong if you added directly 1.72 and 8.02 newtons to find the net force on Q3. Because while F13 is positive, but F23 is pointing in the negative x direction, so we have to put a minus sign on it. So we're all here just in the x direction. So the magnitude of my force acting on my third charge is going to be 1.72 newtons minus 8.02 newtons because the force that charge 2 is exerting on charge 3 is negative, is pointing off to the left. So my net force then is going to be negative 6.3 newtons in the negative x direction. If I were going to label that force in here, the net force acting on charge 3 then is going to be pointing off in the negative x direction, and that's going to have a magnitude of 6.3 newtons. For a workbook problem, you are going to have 3 charges in a row, but they are all going to be positive charges, not a positive, negative, positive charge. And then you're going to have to find the magnitude of the force acting on your third charge. So how would you do that if all of these charges were positive? Okay, so also we're going to call this Q1, Q2, Q3. Well, again, think about the direction that the forces should be between our individual charges. We're thinking about charge 3. Charge 1 and charge 3 are both positive, so the electric force between them is going to be repulsive. That means that the force that Q1 is exerting on Q3 is going to want to push them away. So the force that Q1 exerts on Q3 is going to be pointing off in this direction. So I'll call that F13. Well, let's think about the force between Q2 and Q3. Okay, they're both positive. So the electric force between them is going to be repulsive. They also want to push each other away. So that means that the force that charge 2 exerts on charge 3 is also going to be off to the right. So actually this problem's a little bit easier for you. If you had to find the net force acting on charge 3, then you would also add up the force F13 plus the force F23. But these are both going to be positive forces because they're both pointing off in the positive x direction. So then you don't have to worry about, do I need a negative sign on one of my quantities for the force vector between our charges. You have to really think about, am I a positive or a negative charge? And are the forces between my two charges going to be repulsive or attractive in order to figure out the direction of those forces?